Welcome to the UGC lecture series. In this lecture, we are going to talk about query optimization. Query optimization is one of the important aspects of database management system and in fact affects the speed with which a user gets a response from the database management system. So, the main objectives of this lecture are to give a brief introduction to query optimization, to explain alternate ways in which queries can be evaluated by generating equivalent expressions for the query, and to discuss in detail the methods that are used to estimate the cost of query processing. Now, what we want to do is, unless there are alternate ways in which a same query can be evaluated, there is no question of optimization. Now, if you have alternate ways, then you must have methods to calculate the cost of query processing. So, the less the cost of query processing, that is the expression you have to take, and that way you are going to optimize the query. So, and you have to understand some statistics that is used for estimating the cost of the query. Let us take a simple example to give alternate ways of evaluating a given query. So, you have equivalent expressions and you have different algorithms for each expression. So, for example, if you take this customer name, this is the operation, select branch city is equal to Brooklyn, and then you are taking branch account and depositor. Here what you are doing is selecting the customer name and then you are doing this operation before you select the branch city. So, these are two different pathways of evaluating the same expression. So, an evaluation plan defines exactly what algorithm is used for each operation, how the execution of the operation is coordinated. Suppose you have customer name and you have to sort it to remove duplicates, and this is a hash join, this is a merge join, this is a linear scan, and this uses an index 1. So, this is a pipeline. So, what you do is you start here, do a hash join with depositor, then you merge join, and then what do you merge join? You merge join this branch city is equal to selecting branch city is equal to Brooklyn, which has an index of 1, and branch balance less than 1000, which you need to do with a linear scan on the account field and this on the branch field. These two together you can do simultaneously, that is what is called as pipeline. They are independent things, so you can do it simultaneously. Then do a merge join, and with that whatever the number of tuples you get for the merge join, you merge it with the depositor with a hash join and then find the customer name. So, cost difference between evaluation plans for a query can be very enormous. Okay, it can vary from seconds versus days in some cases. So, depending upon what operation you do first, how you do the operation, how you pipeline it, how you do the join, whether you do the join with less number of tuples or more number of tuples, what are the fields which are common, all these affect the cost of the query, and it can vary very widely between seconds versus days. What are the steps in cost based query optimization? So, generate logically equivalent expression using equivalence rules. We are going to see these equivalence rules as we go along. Annotate the resultant expression to get alternative query plans, and then you choose the cheapest path plan based on what? Based on the estimated cost. So, the cost is what we are going to decide. So, estimation of plan cost is dependent upon many things. One is one main thing is the statistical information about the relation. For example, what are the number of tuples, what are the number of distinct values for the attribute, all these together will decide on which you should do first. So, cost formulae for algorithms are computed mainly using statistics, and statistical estimation for intermediate results are also you do. So, now the first step in a query optimization is, given a query, how do you find equivalent expressions for this? That is the first step. So, how do you translate or transform a relational expression that we have got? Two relational algebraic expressions are said to be equivalent if two expressions generate the same set of tuples on every legal database instance. That is, the order of the tuples is irrelevant, that we are not bothered about, but when we say that two relational algebra expressions are equivalent, we say they are equivalent if they generate the same set of tuples, for every legal database instance. Every instance you should generate the same tuples. However, the order of the tuples we are not considering, even if they are not the same, you still say it is equivalent. In SQL, inputs and outputs are multi-sets of tuples. Two expressions in the multi-set version of the relational algebra are said to be equivalent if the two expressions generate the same multi-set of tuples on every legal database instance. So, what we have done here is, instead of saying relational expression, we are taking SQL. So, two expressions, and in general the input to an SQL statement as well as the output of an SQL is multi-set of tuples. So, what we say is, the two relational algebra expression corresponding to SQL are considered to be equivalent if the two expressions generate the same multi set of tuples on every legal database instance, not for some cases, all cases it should do that. So, in order to do this transformation of a relational expression to an equivalent relational expression, we have to have what is called an equivalence rule. So, what is an equivalence rule? An equivalence rule says that expressions of two forms are equivalent if you can replace one expression in the first form by a second expression or a second expression by the first expression. That is what we called as equivalence rule. Now, we are going to look at each of the equivalence rules. So, first is conjunctive selection operations can be deconstructed into a sequence of individual selections. So, if you have a multi conjunction and operation of selections, you can deconstruct it to form a sequence of individual selections. For example, this you have a selection on theta 1 is a value of a tuple or attribute value, and then you have like this E, or you can write this is equivalent to these two. Remember, this is a selection operation. Remember, in a tuple, for example, you have a customer name of the branch and amount of balance as your 3 fields. When you do selection like this, what will you do? You will say if the branch is equal to say Anna University and account balance is greater than say 5000, then select those tuples. So, now what you are going to do for every tuple here, suppose you have 1000 tuples, all the 1000 you are going to check these two fields. Okay. So, instead of doing that, whether we can do some other method, that is what we are looking at. So, here what you do, you first select the operations, select the tuples that satisfy one of the condition, and then you select from that tuples those that select that give you the next set of operations. So, this is one way of doing this. Selection operations are generally commutative, and then you have this is the operation where you have a set, this is the equivalent relational algebra. So, this is replaced by a single expression. Only the last in the sequence of projection operation is needed, the others can be omitted. Selections can be combined with Cartesian products and theta join. So, it can be done like this. This is select of theta E1 cross E2, Cartesian products can be replaced like this. This is theta join, and similarly you can do like this. So, theta join operations and natural joins also, this is the different rules. So, what we have seen here is the rule of selection. Now, you have theta join. So, theta join you can do any order you can do. So, the smaller one and the larger number of tuples and so on. Natural join operations are also associative similar to theta join. Theta joins are associative in the following manner. So, if you have E1 theta join E2 theta join theta 2 and theta 3 of E3, you can write this as E1 theta 1 and theta 3 like this. Now, why do you want to do this change of the order? The change of the order is done so that you operate with expression that result in less number of tuples for some cases. So, where theta 2 involves attributes from only E2 and E3. So, this is what we are trying to say. So, the pictorial representation of these rules, for example, the rule 5 is like this. So, E1 theta join E2 can be written as E2 theta join E1. Next one, this operation, this can be written as E1 join E2 join E3 can be written as E1 join E2 E3. So, instead of doing E1 E2 first, you can do E2 E3 first, E1 join with that. So, the order in which you do this will be done, the result of this will be joined with this. Here this will be done first and the result of this. Why is this so important? This is important because what join you do, the operation and the cost of the join depends upon the number of tuples that E1 and E2 are associated with. Let us look at this. This is E1 theta join of select, and then with the join you can write the join with the select. So, if you do the selection first, the number here will be less. So, the join operation will be less costlier. So, that is what we are trying to tell here. The selection operation distributes over the theta join under the following two conditions. When all the attributes in theta involve only the attributes of one of the expression being here. So, here the theta is only concerned with this expression, then you can do this. Similarly, when theta 1 involves only the attributes of E1 and T2 involves only the attributes of E2, then you can do it like this. So, that is the seventh operation. What he is saying in this 7b is, if you have a theta here and that theta involves only E2, then you can do both the this select operations before you do the join operation. So, that makes it much more better. Then finally, you have an eighth rule, the projection operation distributes over the theta join operation as follows. So, suppose you have a projection L1 union L2 and you have a theta join between E1 and E2, you can write this as project of L1 E1 theta join projection of L2 E2 like this. So, consider join E1 theta E2, L1 and L2 are be sets of attributes from E1 and E2 respectively. Then this union here you have L1 L2 E1 theta join E2 can be written as project of L1 union L2, project of L1 union L3 of E1 theta join projection of L2 union E4 E2. Now, what is this L3 L4? L3 with the attributes of E1 that are involved in the join condition theta, but are not in L1 union L2, and L4 similarly are the attributes that are involved with E2 that is involved in the theta join, but is not involved in L2 union L1 union L2. So, this is a very different, not a intuitive way of expressing these things. The next rule that you have is the set operations union and intersection are commutative. This is a general rule. Set difference of course is not commutative. Set union and intersection are also associative. So, E1 union E2 union E3 can be written as E1 union E2 E3. Now, the difference comes is that you will do this first. Now, let us assume that you have 1000, 500 and 200, then it makes a large difference in which order you do. Similarly, the intersection. The next intersection equivalence rule is the selection operation distributes over union, intersection and set difference. So, theta the select of the theta is the condition E1 minus E2 is equal to select of E1 minus select of E2, and similarly for union and intersection in place of select of theta E1 minus E2 you can write this as this, and similarly for all these. The projection operation distributes over union. So, suppose you have this projection operation and this union, you can write the projection of this union, the projection of this. So, let us take some example to actually find out what we are trying to do. So, find the names of all customers who have an account at some branch located in Brooklyn. This is the example query. So, find the names of all customers who have an account at some branch located in Brooklyn. So, what we want to find, that is the project operation is customer name, and you want to select who have an account at the same branch, at some branch located in Brooklyn. So, here you are selecting the branches, branch city has to be Brooklyn. Trying to find the customer name of all customers who have an account in a branch that is located at Brooklyn, and here you have branch, join, account, join, depositor, all the three you need in order to find this, because branch will give me which branch is located in which city, account will give me the account is where and the account number, and the account number along with the customer name will be given here. So, let us take the example of 7a. Now, this operation we are going to do. So, let us see what is done. So, you have here project, customer name, select branch city equal to Brooklyn. This is performing the selection as early as possible, reduces the size of the relation, that is join. So, find the names of all customers with an account at Brooklyn branch whose account balance is over 1000, customer name, branch city is equal to Brooklyn, intersection balance is greater than 1000. So, the number of selected will be less. So, this is better. Now, transforming using join associatively, there is an associate. So, do branch into account and then do depositor, the rest of it is the same. Okay. Now, we were looking at this example where here if you look, now what we are doing in this equivalence transformation is we are doing this branch, join, account, join, depositor. We are doing this first before we use it with branch. So, this join associativity is what we have used here. The second form provides an opportunity to apply the perform selections early rule resulting in the sub expression. If you do it this way, you can say branch city is equal to Brooklyn branch join with select balance greater than 1000 account. Thus, a sequence of transformations can be useful. So, if you do this and then do this, you have a sequence of operations that is useful, and this is very important if you want to do the select operations. Here what we are trying to do is, it uses a lot of statistical information as I said. Here we have find the names of all customers with an account at a Brooklyn branch whose account balance is over $1000. Now, here this is a simple query that we have, and we have 3 join operations. Only thing that we have done here is, this was the given, that is the joins are like this. Now, what we do first is, we do not do any change here, but what we do here is we use associatively and club branch and account together and depositor we keep separately. Now, we will understand the reason for this only if we look at the select. Now, what does the select say? Select has something to do with the branch relation and has also something to do with the balance relation with the account relation. So, in order to use this appropriately, we are doing this associative, we are changing it, transforming it. So, this form provides an opportunity to apply the perform selections early, that is one of the main rules. Do the selections as early as possible, so that your number of, when you, what do you do when you do selection? You just reduce the number of tuples. So, suppose you have customer numbers and you have the balance, and if you say you want only numbers tuples whose balance is greater than 1000. So, out of say 2000 records, you may reduce it to 500 records. So, that is where you are reducing the size, and with that if you do a join, obviously the join is going to be less than. So, suppose I want to do a join between 2000 into 1000 and 500 into 1000, lot of difference in the time that is taken. So, select has to be performed as early as possible. So, branch city is equal to Brooklyn branch and branch balance is greater than 1000 account. So, these two will be done, and then after that you will do it with the depositor. So, here is the example of multiple transformation. Here is the initial expression tree and here is the tree after multiple transformation. So, you have project customer name, select branch city is equal to Brooklyn and branch is less than 1000. Join branch account and depositor, account depositor you first join and then join it with branch. Now, we have changed this like this. What we have done is, first using this associative we have joined account and branch instead of account and depositor, depositor we are leaving as it is. Now, when we do this, this branch, now remember these two are an AND condition. So, branch city is equal to Brooklyn, this reduces the number of tuples that we have to deal with in the join operation for the branch relation. This decreases the number of tuples that you have to deal with in the join operation between branch and account in the join operation. So, this we do, and so the number of tuples you get after the join operation will be much lesser than the number you would have got by joining all these three. After you do that, then join it with the depositor, then project and get customer name. So, this is after multiple transformations. The first transformation you do is you use associative and branch and account you put together and depositor you put to separately. Then introduce the selection as early as possible. So, introduce the selection here, introduce the selection here. You can't do that all the time, this is because it is a meet and an AND condition along with the join. So, you do that and you get. So, this is what you did. So, what we do actually is, first we find out the customer name when branch city is equal to Brooklyn, this is the branch account, and then you do branch account and then you obtain a relation whose schema is branch name, this is after this branch name, branch city, assets, account number and balance. This is the result of combining or doing the join relation between branch and account, but we are only getting those tuples for which branch city is equal to Brooklyn. Then you push the projection using equivalence rules 8A and 8B. Let us just look at 8A and 8B just for a reference. So, this is 8A theta and this is 8B. So, let us do that. That is what we did. We have seen the example. So, what we do is customer name, project the customer name, project the account number, branch city is equal to Brooklyn branch into account into depositor. Performing the projection as early as possible reduces the size of the relation that has to be joined. So, for all relation, size of the relation, not the size number of tuples, but the size. So, projection actually allows you to, so here for example, here we had all this branch name, branch city, assets, account number, balance, from which we are taking only the account number along with the and then doing this. So, two things we are doing, we have to push the selection as early as possible and we have to do the projection also as early as possible. Pushing the selection reduces the number of tuples associated with the relation and pushing the projection reduces the size of the or the number of attributes associated with the relation. So, join ordering example, for all relation R1, R2, R3, you can have R1 join R2 join R3 or R1 join R2, R3. This is called as join associativity. If R2, R3 is quite large and R1, R2 is small, we choose this, so that we compute and store it in a smaller temporal relation. So, consider this expression, customer name, branch city is equal to Brooklyn, the same example, could compute account depositor first and join result with branch city is equal to Brooklyn, but account deposit is likely to be a large relation. Only a small fraction of the bank customers are likely to have accounts in branches located in Brooklyn. So, it is better to compute branch city is equal to Brooklyn branch and then do the account with it. So, query optimizers, so that this is the enumeration of equivalent expressions. Query optimizers use equivalence rules to systematically generate expressions equivalent to the given expression, can generate all equivalent relations as expressions as follows: apply all applicable equivalence rules on every equivalent expression found so far, add newly generated expressions to the set of equivalent expressions until no new equivalent expressions are generated. So, you apply all the 12 rules that we saw. But however, to do this automatically, the above approach is very expensive in both space and time, because you have to store the intermediate results. So, two approaches are optimized plan generation based on transformation rules and special case approach for queries with only selections, projections and joins. So, certain things we are going to do. So, implementing transformation based optimization, what we do is, when E1 is generated from E2 by an equivalence rule, usually only the top level of the two are different, subtrees below are the same and can be shared among using pointers. So, if you have E1, E2, only this top level of the two are different, the subtrees are the same, so you can reuse it. So, same sub expression may get generated multiple times. So, there is need to detect duplicate sub expression and share one copy. Time requirements are reduced by not generating all expressions. For this we do dynamic programming. We will study only the special case of dynamic program for joint order optimization. So, that is very important. Now, let us look at cost estimation. So, cost, now we have done all these ordering, we have got some equivalent expression. Up to this point we were looking at only that given a query expression, how can I get the same result for every legal database instance with an equivalent expression. So, that is what we have seen. Now, which of these equivalent expressions should I select? That is the next point, and for that I need to know the cost I must know how to do the cost estimation. So, cost of each operation operator of this is described, and you need statistics for of the input relation. So, basic two things you need is the number of tuples associated with each relation and the size of tuples. The size of tuples means it could be the number of attributes as well as the type of attributes also. So, integer, real, character, string, size and so on. So, inputs can be results of sub expressions. You need to estimate statistics of expression results. To do so, we require additional statistics. One important additional statistic is the number of distinct values for an attribute. So, if a attribute has distinct values are very important. Okay, the number of distinct values. So, three things we said are important. One is the number of tuples associated with the relation. Second, we said the size of the tuples. The size means the number of attributes as well as the type of attributes, because the type also determines the number, as well as additional statistics which says what is the number of distinct values that an attribute can have. So, the choice of evaluation plans, you must consider the interaction of evaluation techniques when choosing evaluation plans. Choosing the cheapest algorithm for each operation independently may not always yield the best overall algorithm. Just because every time you will choose the one that is the cheapest for each operation, independent of what other operations are done in it, may not give an overall cheap result. So, merge join may be costlier than hash join, but may provide a sorted output which reduces the cost of the outer level aggregation. So, this is very important. Nested loop join may provide opportunity for pipelining. So, if these two are there, then overall it will reduce, though independently it is more costly. Practical query optimizers incorporate elements of the following two broad approaches. Search all the plans and choose the best plan in a cost based function, and then use heuristics to choose a plan. So, to find the best join tree for a set of n relation, to find the best plan, what do? You consider all possible plans of the form S1, where S minus S1, where S1 is any non-empty subset of S, then recursively compute cost for joining subsets of S to find the cost of each plan. Choose the cheapest of the 2 power n minus 1 alternatives. Best case for recursion is single relation access plan. For example, let us look at left deep join trees. Now, in left deep join trees, the right hand side input for each join is a relation, not the result of an intermediate join. Okay. So, here in the left deep join tree, the right hand side input of each of these joins is a relation, but it is not the result of an intermediate join. But if you look at this one, here you have R1 R2 join, Okay, so, this is a result of an intermediate join, this is added with R 3 and then R 4 R 5 is this is an intermediate result, this is an intermediate result, these two are joined with this. With dynamic programming, time complexity of the optimization with bushy trees is of the order of 3 power n. With n equal to 10, this number is 59,000 instead of 176 billion. So, space complexity however is the order of 2n, this is between these two trees. To find best left deep join for a set of n relation, consider n alternatives with n relation as the right hand side input and the other relation as left hand side input. Modify the optimization algorithm, replace for each non-empty subset S1 of S such that S1 is not equal to S by for each relation R in S, let S1 be equal to S minus R. So, consider the expression R1 join R2 join R3 with a common A as the common attribute. An interesting sort order is a particular sort order of tuples that could be useful for a data operation. So, use merge join to compute R1 join R2 and this may be costlier than hash join, but generates results sorted on A, then which in turn may make merge join with R3 cheaper, which may reduce cost of join with R3 and minimize overall cost. Sort order may also be useful for order by and grouping. So, depending upon the type of query you are going to use later on, the way in which the tuples are ordered is also important. So, this question of whether to use a merge join instead of a hash join, merge join will give you a sorted output, while hash join is cheaper, but does not give you a sorted. Depending on whether you want the sorted or not, this is going to this choice is going to decide. Now, if you do a merge join and then do a join with that is cheaper than doing a hash join with hash join. Okay, so, this all these are considerations that you have to consider. So, cost based optimization is expensive even with dynamic programming. System may instead of using the actual cost based optimization, doing it, generating it, it may use some heuristic to reduce the number of choices that must be made in a cost based function. So, heuristic optimization transforms the query tree by using a set of rules that typically, but in not all case, improve execution performance. So, the two ones which we saw in the example, perform selection early reduces the number of tuples, perform projection early reduce the number of attributes, which I have already spoken about. Perform most restrictive selection and join operation with the smallest result size before other similar operations. Some systems use only heuristics, others combine heuristics with partial cost based optimization. Many optimizers consider only left deep join orders plus heuristics to push selections and projections down the query tree and reduces optimization complexity and generates plans amenable to pipeline evaluation. Now, the question is if you do optimization like this, if you do optimization it is good, but you should not spend too much time in doing the optimization. Heuristic optimization used in some version is pick best relation to join next and so on. Some query optimizers integrate heuristic with alternative access plans, and some optimizers apply transformation to entire query and do not depend on the block structure. So, even with the use of heuristics, sometimes it is very query optimization will improve the will impose a cost. So, it will make sense to use query optimization only when the query itself is very expensive. I spoke a little bit about the statistics information for cost estimation. So, it depends on the number of tuples, number of blocks containing the tuples as memory, size of the tuple, the blocking factor and various things. So, if the tuples are stored physically in a file. So, the histogram on attribute age of relation person is like this. So, here you see that certain values are more number of tuples are available. So, you have to do a selection of size estimation, and the selection size estimation is given like this. Let C be the the number of tuples satisfying the condition. You have to find the minimum and the maximum, and according to that histograms are available and you can refine the estimate. Size estimation of selections is also there. We are not going to go into the details here, and you can also look at disjunction and negation. There are estimated costs for how many tuples will, how to find how the tuples affect the relation. So, example, suppose you have customers 1000 and this is 25, which implies the average customer is this, depositor 5000 and so on. So, with this information, which implies that on average each customer has 2 accounts, because number of depositors 5000, and customer name depositor is a foreign key and this is the primary key. You can estimate the size by looking at the distinct values, and estimation of distinct values are straightforward for projections and for grouping and aggregation. In this lecture, we have spoken about issues in query optimization. We have explained alternate ways in which queries can be evaluated. We have looked at short look through on how cost of query is important and how the statistics can be used in query cost estimation. what I want you to do is I want you to discuss 2 alternative query evaluation plans for 2 illustrative examples. I want you to give a pictorial representation of equivalent relations of joins. I want you to discuss the equivalent rules of set operations and explain in detail how ordering of operation can affect the cost of queries, and also how statistical information can be used for query cost information. Thank you.